Now let us consider gravitational force. So what are these gravitational forces? Let us imagine two bodies of masses m1 and m2 separated by a distance d. The force of attraction between these two bodies F is found to be directly proportional to product of their masses and inversely proportional to square of the distance. Therefore, if I combine F proportional to m1 m2 by d square, so proportionality can be replaced by a constant capital G, m1 m2 by d square. So this is the attractive force present between two bodies of masses m1 and m2 separated by distance d. This is called inverse square law. The gravitational force of attraction between two bodies is always only attractive. There is no question of repulsive. So gravitational force is attractive force and it is equal to G into m1 m2 by d square, and G is a constant called universal gravitational constant. Capital G is called universal gravitational constant. The universal itself represents this is independent of any other quantity. It is always constant wherever you take the body on any planet, any place, any medium, this value remains same. That's why it is called universal gravitational constant. Here the value of G is found to be 6.67 into 10 to the power of minus 11 Newton meter square by kg square. The universal gravitational constant is 6.67 into 10 to the power of minus 11 Newton meter square into by kg square. So if you take the dimensional formula, this dimensional formula is m power minus 1 L cube T power minus 2. That means the negative dimensions of mass. The only physical quantity in the first year total physics which has negative dimensions of mass, universal gravitational constant m minus 1. Now why it is taken as universal law? This gravitational constant law itself is called universal gravitational law because the force between two bodies is independent of matter present between them. Whether any material is present between these two or medium present between these two, on all those factors the force is not going to depend. Whatever the medium is present, even if the materials are present here, the force between these two is G into m1 m2 by d square. That's why it is called universal law. It is constant wherever you take. G is anyhow constant, the remaining effect is also not there. Now if I take the forces between two particles, say m1, m2. m1 attracts m2, let us say with force F1. Here m1 is attracting m2. m2 is attracted by m1 with force F1. If I say m2 also exerts attractive force on m1, say force F2. So between two bodies there are two forces. F1 is the force exerted by m1 on m2. F2 is the force exerted by m2 on m1. These two are definitely equal in magnitude and opposite in direction. They form action-reaction pair. The gravitational forces present between two bodies always form action-reaction pair. They are equal in magnitude and opposite in direction. They always act along the line joining the two bodies. This is the line. So maybe along this side or this side, only along the line joining the two bodies they act. They are called central forces. Central force in the sense they always act along the line joining the two bodies. Now suppose two bodies separated by this distance, say m1 and m2 are taken, the gravitational force between them is, let us say, F. Suppose if I introduce a third mass m here, a third mass m is introduced between them. Is there any effect on the force between first two? I'll consider only these two. Is there any effect on force between these two? No. Introduction of other masses does not affect the force between first two. The net force on each body may change. Previously m1 is attracted by m2. Now it also gets attracted by m also. Suppose if I take net force on m1, net force on m1. Previously it is attracted by m1. m1 is attracted by m2 previously. So let us call that as m1 m2. Now in addition to this, there will be another attractive force with m. So the total force on m1 changes, total force on m2 changes, but force between m1 and m2 remains constant. So introduction of the other masses does not affect the force between first two. Now suppose m1 and m2 are taken, force is F. Initially, let us say this is air, total is air medium, force is F. Now if I replace this with water, the two bodies are placed in water. Now what is the force? Again F only. So even if you change the medium between the two bodies, the forces remains the same. Force is not going to be affected. And also very important thing, gravitational force is a conservative force. Conservative. Because work is independent of the path along which you are moving. So whatever the path you follow, the work remains same. That's why this force is said to be a conservative force. The gravitational forces are conservative forces. Suppose at any point I want to calculate the net force. A number of masses are taken and we are observing the net force acting on one body. So by using superposition principle, we can calculate the net force. It's a vector addition only. For example, if I take three particles at three corners of an equilateral triangle, say M, M, M. Question is, what is the force on this particle? So this M attracts this one, this M also attracts. So take the angle between these two and find out the resultant. Calculate F dash. This is the resultant force. This is what we call vector addition. By following vector addition, we can find the resultant force acting on the bodies. So whenever we consider a mass, definitely like a charge, positive charge or negative charge or a magnet, north pole or south pole, surrounding the mass, up to what maximum distance its influence is felt, that the space surrounding a mass in which its influence is felt is called gravitational field. This is gravitational field. Gravitational field is like electrostatic field or magnetic field. Like this is also the space surrounding the mass in which its influence is felt. Theoretically, it extends up to infinity, because one mass will have influence on the other mass even if the distance of separation is infinity, because F inversely proportional to d square. When d is infinity, then F becomes 0. Therefore, the gravitational field surrounding a body always extends up to infinity distance. If I place a body here, say unit mass, m is equal to 1 is placed, the force acting on this unit mass F is given by g into m into 1 by d square. So this is called gm by d square, gravitational intensity. I is equal to gm by d square. Like electric intensity, magnetic intensity. We can also define gravitational intensity, which is equal to gm by d square.